Okay, got that going. Today we're mostly going to be interested in projectile motion. What's projectile motion? It's the motion of something you project through the air, something you throw, projectile motion. So when I throw this marker, we're talking about its motion, projectile motion. We call the path that a projectile follows out its trajectory. So the trajectory of the object. So that's mostly what we're interested in talking about in these problems. We're going to ignore air resistance. We're going to assume that you're throwing it in a vacuum, that kind of stuff. So that's the main focus of today and what we'll spend most of our time on. But we're going to work up to it because we're going to be redoing stuff we already did, but this time with vectors. And we did a little bit of this last week, but we'll re-go over definitions real quick using our vectors, rewrite the kinematic equations real quick, and then jump into, do an example, then jump into projectile motion. Okay, so back to basic definitions. First off, when we're tracking your position, when we use a position vector, how do we set up the position vector? We set it up like this. Your position vector is your x coordinate times I hat plus your y times j hat plus your z times k hat. Where x gives me your x position at any time, y gives me your y position at any time, and z gives me your z position at any time. Yeah. Throw those three together in a vector, you got your position vector. Makes perfect sense, right?
Yep.
Typically, we'll just be working in 2 dimensions, but it's better to show you the definitions in 3 dimensions, because it's easy to go from 3 dimensions to 2. Okay, definition now of your average velocity vector. What's your average velocity vector? It's your change in your position vector over time.
Is your camera going?
I thought so. I heard the... Yeah?
Oh, I just can't see it.
I keep the screen dark so it doesn't die on me.
Just
Oh.
making sure.
Okay. Yeah, we should have a lot of camera issues cleaned up. My phone built up like a bunch of garbage storage. So my memory was slowly being eaten up, so I completely swiped my phone.
Oh.
And so back to like 40 gigs of free memory.
What does the R stand for in this? Is it just your position?
It's just your position. We just need a letter. We can't use X, Y, and Z because we still want you to know to use those the way you know and love. So we need something to mark your position.
Okay.
R is as good as anything. Okay, average velocity. Average velocity is your displacement over time. The change in your position vector over time gives you your average velocity vector. Notice these are always vectors. Because your average velocity has an average speed and the average direction you were going in.
Okay.
Make sense?
Yeah.
Okay. Now, here's the crucial part. Notice how average velocity is calculated. So this is the change in r vector over delta t. Or we can think about it as 1 over delta t times the change in r vector. You with me so far? Notice that this is a vector, and this is just a scalar. Okay. So your average velocity, what direction does it point in? It points in the same direction as your change in r vector. Those point in the same direction. That's the crucial point. The average velocity is this same vector scaled by some number. So it's in the same direction with just a different scale.
Okay.
You follow that? So let's draw a picture of this just to make sure it's crystal clear. So imagine here you are, you're trotting out this path. Good?
Mm-hmm.
After 1 second, you're right here. After 2 seconds, you're right here.
Okay.
So here's your R1 vector. This is your position vector at time 1. This is your position vector at time 2.
Okay.
Good? Your displacement vector then, your change in position vector, is this vector which starts here and ends here. Notice that it's pointing in the same direction that you're going.
Why is that?
Well, that makes pretty good sense. If my velocity is that way, that's the way I'm moving.
Oh, okay.
Okay. That's the crucial point. But why is that? Why is that by definition? Notice that your change in position, you change your position in the direction you're going.
Okay.
Okay, so that's a crucial point. It's in the same direction as your delta r vector, just scaled. So now, if you take the limit as delta t goes to 0, so now when we're defining velocity, that's the limit of your change in your, not change in v, change in r, change in displacement over time gives you velocity, right?
Yeah.
Take the limit as your change in time goes to 0, or in other words, take r2 and make it closer and closer and closer to r1, right?
Okay.
In the limit, what happens to this vector? What happens to its direction?
Doesn't the direction stay the same?
No, notice right now it's not quite a perfect tangent. In the limit, so here's your path, here's the position vector we're talking about. In the limit, your velocity vector will always be perfectly tangent to your path.
Tangent to your path.
Tangent to your path.
How do you know what tangent to the path looks like?
It only, if we draw the line, it would only intersect your path at one point, but it's going that way.
Oh, I see.
It's perfectly tangent to your path. Over here, notice your path. I'm going to draw your path in with a solid line now so you can see it better. Here's your path. Notice that this velocity vector pointing this way, your average velocity vector isn't a perfect tangent. But that's because it's an average velocity. When we're talking about your instantaneous velocity, it's always perfectly tangential to your path.
Okay. Okay.
Does that make sense?
I think so.
Yeah.
Okay, so now when we define average average acceleration, how do we define average acceleration? It's the change in your velocities over time. Makes sense, right?
And your velocities over there. Okay.
Acceleration, change in velocity over time, which is change in your velocity over time, which is some scalar times your change in velocity vector. So once again, notice that your acceleration vector, your average acceleration vector, points in the exact same direction as your change in velocity vector. It just has a different scale.
Okay.
You follow that?
Yeah.
So let's draw a picture one more time. So now this dotted line is your path. You with me?
Mm-hmm.
So at this point, your velocity is tangential to the path, so it's straight up. And at this point, your velocity is tangential to the path, so it's like that.
Okay.
Okay, so now take those two vectors. Let's redraw them right there. I know my picture lies a little bit, but make sure you understand what I'm trying to show. So there's v1, there's v2, redraw them right here. My change in velocity vector then is this velocity vector right here.
How do you know where that's pointing now?
I try to keep them pointing the exact same. It's like I'm picking it up and putting it there. So I'm not twisting my vectors at all.
Yeah, but it's going this way, which isn't where your path is going at all.
Right, my average velocity vector is not the way, my change in velocity vector is not the way my path is going at all. Perfect.
And it won't ever?
It could be.
Why not?
Here's my velocity here, agreed. Here's my velocity here, agreed.
Yes.
Here's our change.
I see that, and I agree with that. I'm saying, like, why isn't it
Well,
pointing with where your path is going?
First, wrap your head around the fact that it's pointing differently.
Okay.
Okay, so this is a direction not of our velocity, this is a direction of our acceleration.
No, it's delta velocity.
It's your change in your velocity. So it's not your velocity at any time, it's your change in velocity.
Okay.
So the change in my velocity from here to here is that thing. But notice that my average acceleration points in the exact same direction as this vector.
And your average acceleration is pointing this way?
So my average acceleration during this time frame is pointing this way, roughly.
Okay, I see that.
So what does that mean? First, let's think about intuitively what acceleration is. What's acceleration? It's your change in velocity.
Yeah, you're speeding up.
That's one way I can change my velocity. One way I can change my velocity is I can speed up. What's the other way I can change my velocity?
Slow down.
I can change my speed. That's one way I can change my velocity. What's the other way I can change my velocity?
Direction.
I can change my direction also. So anytime I change my speed or my direction, there has to be an acceleration. Those are changes in velocity. Acceleration is change in velocity.
Okay.
You with me?
Yeah.
And so here, we didn't really change our speed much. We were just kind of turning. And so on average, we were turning that way.
On average, we're turning that way.
Our average between here and here was just turning this way.
Okay, I see what you're getting at.
And that's what my acceleration vector is telling me.
Okay.
Now, let's say I would have sped up a lot also at the same time. So let's pretend v2 was a lot longer. So my speed got a lot bigger too, right? That would make this one a lot longer. And so now my change of velocity vector would be pointing this direction. And so the average acceleration then would look more like this. Because not only are we turning that way, but we're also speeding up that way.
Okay.
Make good intuitive sense?
Is the direction when you're on like a vector graph just between positives and negatives, or does it go up and down as well?
Direction. Sorry, I didn't understand your question. Look, I'm going to undergo an acceleration. I didn't change my speed, I just turned.
Yeah. How does that look on a graph?
A graph of what?
One of those.
On a position? On a.
Yeah.
How does the acceleration
How
look?
do you specify how much it's changed by speed and how much it's changed by direction?
Oh, we'll figure out how to do that. How much of you change the speed, how much of you change the direction. Perfect. So when we break, so let's say that we're at some instant in time. At some instant in time, we'll say that my velocity vector looks like this, and my acceleration vector, let's keep it really, really simple for our first case.
Okay.
So let's say at some instant in time, my velocity vector looks like this, and my acceleration vector looks like this.
Okay.
So my path might be something like I'm currently moving up, and I'm speeding up, and I'm going to turn like that. So here's what my path is going to be. At this exact instant, I'm moving that way, I'm accelerating that way, so later in time, I'm going even faster, and I turned. You with me?
Yeah.
This is velocity, this is velocity. Here's my acceleration at this point. We'll just focus on my acceleration at this point. So I can break my acceleration vector up into two components. I can break it up into the component that's in the same direction as my velocity, and the component that's that's perpendicular to my velocity.
Okay.
The component that's perpendicular to my velocity is the component that goes towards your change in direction. The component that is parallel to my velocity is the component that goes towards my speed. Let's try another picture. Let's try two simple cases so that we can see each of them, where all my acceleration is perpendicular and all my acceleration is parallel. Okay, so let's say just moving in a straight line.
Yeah.
So if you're just moving in a straight line, let's say here's v1, and later your velocity is this, v2. With me?
Yeah.
Then this right here is your difference in them. This is your delta, so this is also your acceleration. And all your acceleration went towards speeding you up.
So your delta v is your acceleration then?
Acceleration is change in velocity. Instantaneous acceleration is instantaneous change in velocity. Average acceleration is average change in velocity.
Okay.
You with me on that one?
Yeah.
Okay, that one's pretty intuitive. Now let's think about a simpler or a more complex case, but we'll make it as simple as we can. We're going to assume that you're walking along a curved path, but you're not changing your speed.
Okay.
So your speed stays exactly the same. So your velocity here is like that, v1, and your velocity here is like that, v2, and they have the exact same change in speed. Or the exact same length, it's just a change in direction.
Okay.
So if we try and draw those two next to each other, it's going to look something like that, right? Here's V1, here's V2. Just take those and stick them right there, right there. Don't change their length, don't change their direction. Just change their starting point so I can look at them and
Why
figure
don't
out.
you put them on top of each other?
So I can figure out delta V. Because here's delta V. It's this vector.
Okay. Why pointing down?
Exactly. So my average acceleration was pointing straight down this time. All your acceleration went into the fact that you were turning. Which way were you turning? That way.
Okay.
You're not speeding up, you're not slowing down, you still have acceleration. All your acceleration is perpendicular to your velocity.
Perpendicular.
When it's parallel to your velocity, pointing in the same direction, that's speeding up and slowing down. When it's perpendicular, that's changing direction.
Perpendicular to what?
Your velocity.
So your V1 or your V2?
Well, take the limit as those get closer and closer together, and what happens?
I don't know.
So as V2 gets closer and closer to V1, they end up pointing closer and closer to the exact same direction.
Oh, yeah.
So your picture looks more and more like this. Here's V1, here's V2. Draw the arrow between them. That's almost perfectly perpendicular. And in the limit, it is perfectly perpendicular.
Okay, I see.
Okay, so for any acceleration vector, so now if this is my velocity at some instant in time, and this is my acceleration at some instant in time, here's my acceleration, here's my velocity. I can break my acceleration up into two vectors. I can treat it as this vector, and I can treat it as this vector. This is the acceleration perpendicular to my velocity. This is the acceleration parallel to my velocity. This portion of acceleration is going into speeding me up or slowing me down, depending on its direction. And this one is going into turning me.
Okay.
So that will be a common thing that we do. We take some acceleration and we look at the component of acceleration parallel to our velocity and the component of our acceleration perpendicular to our velocity.
Yeah.
Make sense?
Mhm.
Okay. So, got our heads around the definitions. Now let's quickly re-go through kinematic equations. Make sure we understand these equations because these are going to be the equations that we use for parabolic motion over and over and over again. Okay, so how did all these equations start? It started with the assumption that A is a constant. That's all we assumed. So I said A is equal to A. So, grab one of these. If A is equal to A, where A is a constant, maybe remind ourselves over here we're talking about function. A sub t is equal to A. Then what's my velocity? We take the integral.
Yeah.
If acceleration is a derivative of velocity, velocity is the integral of acceleration.
Yeah.
And so our velocity at any time is going to be A times t. We're going to integrate with respect to time. Maybe just completely write it out one time. So vt then is going to be the integral of A sub t dt, which gives me that v of t is equal to at plus v naught. Some constant. And that constant is our velocity when you plug 0 into this equation. Because when I plug 0 in for time, that term goes away and we're just left with this constant. So I call it v naught, that's our velocity when you plug in 0 for t. Right?
Yeah.
Once again, we can also say that x of t is equal to the integral of our velocity function with respect to time. Or in other words, x at any time t is equal to 1/2 at squared plus v naught t plus x naught t, or plus x naught. Where x naught, why do we call it that? If you plug in 0 for time, you just have this constant. So it's what x is equal to when you plug in 0 for time, x naught. Good?
Yep.
Now, definition of average velocity. There's two ways that we can think about your average velocity. Your average velocity, we can think about one as your change in position over time. That gives you your average velocity.
Okay.
If I go 500 miles in 5 hours, what's my average velocity?
100.
100 miles per hour, assuming I just keep going in the same direction, right?
Yeah.
We're thinking about one-dimensional motion here in driving these.
Okay.
Okay, and another way that we can think about your average acceleration is it's the average of your start and your end acceleration, or velocity. Sorry, average, I think I said acceleration. I meant velocity. Your velocity is the average of your start and end velocity. When acceleration is a constant, because then your velocity function is always linear. It's always a line. If I take any line, and I know the height here, and I know the height here, how do I find the height here? I take the average of those 2 points.
So,
Okay, so I know that this is equal to this. Solve for x minus x naught. In other words, put the t over there. So we get x minus x naught is equal to 1/2 v naught plus v times t. And probably specify that we re-derived a bunch of these equations. So this equation, that one's right there. This equation, that one's right there. This equation, that one is right here. And now this equation. Let's see if I can remember the fast way to do this. We know that acceleration is equal to acceleration.
okay.
Yeah.
So I know that velocity times acceleration is equal to acceleration times velocity.
Okay.
Good?
Yeah.
Okay, treat them as differential, so we cancel out the dt on both sides. So that means v dv is equal to a dx. So I have v dv is equal to a dx. We're going to integrate both sides from 0 to t. Integrate from 0 to t. What do we get? On this side, we get, well, basically we have v squared over 2. We need to evaluate that from 0 to t is equal to, remember, a is just a constant.
Yeah.
So that's ax evaluated from 0 to t, which gives us that. When you plug in t for velocity, we typically just represent that as what we mean by v. So that gives me v squared over 2 minus, when we plug in 0, that's what we mean by v naught squared over 2. Writing too big. Let's write down here. So that gives me that v squared over 2 minus v naught squared over 2 is equal to a times x at time t is what we mean by x minus x at time 0 is what we mean by x naught. Right?
Okay.
Multiply both sides by 2. So let me rewrite that up here now. We'll write smaller. So that gives me that v squared is equal to v naught squared plus 2a x minus x naught. So multiply both sides by 2 is how we get the 2 there. And then move the v naught squared to the other side.
And that's your last one.
And that's the last of our 4 equations where acceleration is a constant.
So whenever acceleration is a constant, we can use any of these to find anything we want.
Any of these 4 equations, yes.
Okay.
And in any direction you want. This is in the x direction when you know the acceleration in the x direction is a constant. Same thing if the acceleration in the y direction is a constant, replacing all our x's with y's, and same thing in the z direction. So we just focused on the x direction here.
Okay.
Make sense?
Yeah.
Yeah.
Now, keep in mind, even though your acceleration in the y and z direction might not be constant, if your acceleration in just the x direction is constant, you can still use these equations for the x direction. Make sense?
Can you say that again? Sorry.
Even if your acceleration in the y and z direction are not constant, and only your acceleration in the x direction is constant, you can still use these equations.
But you would
You
only
can
use
focus
it
in
for
one
x.
dimension at a time. Focus on the x dimension. If in that dimension, acceleration is a constant, you can use these equations. Same with the y, same with the z.
Okay.
Make sense?
I think so.
Okay. So, awkward white space because of class last night. So now we'll move over to the whiteboard. This stuff. Camera here. And then this example problem we're doing, it's the same example problem we started last week, or did last week, but extended some. I don't like that. It's an ugly angle. Oh well. Okay. So, last week's problem, what was the problem? The problem is, here you are at whatever, base control, and the Mars rover is going out on the surface of Mars following some path. Okay, so the black dotted line here is a path that the rover is taking. With me? Okay, and it was given to us what our position vector is. Our position vector, so the position of the Mars rover at any instant of time, is given by this vector.
Of the Mars rover or of us?
Of the Mars rover. We're sitting here watching it. The Mars rover is following this path. We're describing its motion.
Gotcha.
Okay, so this gives us the position of the Mars rover at any time. Notice this is a completely two-dimensional problem.
Yeah. Can you help me make sense of that vector again? Is it the x and the y coordinate?
This gives me the x-coordinate at any time. This gives me the y-coordinate at any time.
That makes sense.
So, let's really quick start solving for where this thing is at some times. So the first question is, where is the rover at time equal to 0, at 0 seconds? Ignore the picture for a second, just solve it.
Okay, then it's just 2.
Just 2 comma
2
0.
comma 0.
Yeah.
Yeah. So our position vector at time 0 is 2 comma 0, and you'll notice that I drew that in.
Okay.
Okay, what's our position vector at time 1?
7 fourths, comma. Is that 1 over 40?
That's 1 over 40.
So it's 41 over 40.
41 over 40. So notice that's going to be 7 fourths is going to be not quite 2. 41 over 40 is going to be almost indistinguishable from 1.
Okay.
Okay? Now let's find your position after 2 seconds, or the Mars rover's position after 2 seconds.
1 comma 8 over 40.
It's 5.
5.
But he was just saying it cancels out, leaving a 5 in the denominator.
So 1/5 plus 2. Right?
Uh-huh.
So 11/5.
11 fifths. Which is going to be a 5th over 2. So somewhere up there, over 2, x direction 1.
Yeah.
Okay.
Good with the picture so far?
Yeah.
Okay, so the next thing we were supposed to do in this problem then was find our velocity vector. What does our velocity vector now look like?
It's just
The integral, or the derivative.
The derivative. So what is it?
wait, isn't it the derivative of? Oh, you have it. Yeah. Okay, we're good. It's 1/2 t.
Negative 1/2
Negative 1/2 t.
t, comma.
And
1 plus
Let me write that smaller.
3 over 40.
Negative 1/2 t, comma, 1 plus 3 over 40
T squared.
t squared.
Yeah.
Perfect. So there's our velocity vector. What's our velocity at time equal to 0?
0 or 1 or 0.
No, 0.
0, 1.
Yep.
Notice that's a vector pointing straight up 1 unit.
Mhm.
And my dotted line isn't perfect, but notice it looks like it's pretty close to tangent to the path of motion.
Okay.
Good?
Yeah. Yep.
Okay, next, what's our velocity at time 1?
Negative 1/2 and then positive 43 over 40.
So that's a vector that points up, basically 1, and to the left, minus 1/2. Or to the left 1/2, right? So it's going to go up 1 and to the left about 1/2. So there it is. Notice once again, tangential to the path of motion.
Over 1. Okay, I see it.
Okay. So v2 then, our velocity at time 2, what's that?
Just -1. And what is that? 13/10.
So again, up a little more than 1, to the left exactly 1. Up a little more than 1, to the left exactly 1.
Why are you drawing these on the vector of R1 and R2?
I don't understand the question.
See how
R
vector
points
R1
to your current position.
Yeah, points to
Why do you
The velocity points out the velocity at that instant. When you're right here, what's your velocity? It's this. When you're right here, what's your velocity? It's this. When you're right here, what's your velocity? It's this.
Is it because your times are the same? So V2 and R2 and your time is both 2? Because
Oh,
your
that's put a
V3
3.
lies.
That's a V2. Was that the question?
Yeah, that's what I was wondering.
Okay. Yep, that was just a typo on my part. Okay. So now,
Okay.
let's look at acceleration. So what is our acceleration vector?
It's the derivative of
So
the
what,
velocity.
-1/2? And
6 or 3/20 e.
3/10, right?
3/20ths.
Well, 6/40, okay, 3/20 t.
So there's our acceleration. Notice we have a constant acceleration in the x direction, but not in the y direction.
And you just have to have one or the other.
No. That means in the x direction, I can use those equations. In the y direction, I cannot. Now, we're not using those equations here. I'm just pointing that out.
Okay, that makes sense.
Good?
Yeah.
You're saying in the x direction you can use that for any position, any velocity, or any acceleration in the x direction.
Those equations perfectly hold in the x direction. When you plug in for your acceleration, minus 1/2.
Okay,
Okay. So now, what's your acceleration times 0?
just -1/2 0.
What's your acceleration at time 1?
-1/2 3/20.
And what's your acceleration at time 2?
-1/2 3/10.
So notice that every single one of these vectors is going to have, well, now let's just draw one of them out. We're going to kind of be overlapping our drawing, so that's why I didn't want to draw them until the very end, because now we're going to make a mess of our drawing. If I draw my acceleration vector here, it's pointing to the left 1/2.
Yeah.
Not down 1/2?
X. My x is 1/2, my y 0.
Yeah.
It's going negative 1/2 in the x
Okay,
direction,
I see.
0 in the y direction. So this vector is pointing this way.
Okay.
In other words, at that instant of time, all your acceleration is in the fact that you're turning. At this instant of time, our rover is not speeding up or slowing down. It's simply turning as it's driving.
How do you know that again?
Because all the acceleration is perpendicular to my velocity vector.
To your velocity vector. Okay.
Yes.
Okay.
Make sense?
And you're saying just that instance, that's not happening.
That's just at that instant time. Its exact acceleration at that instant time is right here.
Okay.
No longer just averages. We're talking about exact. Okay. At R1, its exact acceleration, 1/2 in the x direction, and then 3/20 in the y direction. So it's speeding up a little bit, but still turning a good amount.
Yeah.
Well, Yeah. So, right here, we're still going 1/2 this way. So that's going to be about right there, and then I got to go up 3/20. So very roughly, it's going to look something like that. Here's our acceleration vector.
Okay.
Okay.
Make sense?
Mm-hmm.
Then finally, our last acceleration vector is going to be kind of the same thing, except for pointed up even more. So over 1/2, I don't know, something like that. That's our acceleration at that time. Just draw a picture to try and give you a sense for each of these. Good?
Yeah.
Now, our final problem was, at V2, we were supposed to find our acceleration perpendicular to, and our acceleration parallel to, our velocity at time 2. So at this instant of time, I want to know how much I'm speeding up and how much of my acceleration is going into turning me.
Isn't that just your x and your y for A2?
No, no, no. My acceleration in the same direction as my velocity goes towards speeding up. Not my acceleration in the y direction. Y isn't necessarily speeding up, x isn't necessarily speeding up. At this instant, x was turning because the y direction was my velocity.
Okay.
The y direction is no longer my velocity. My velocity is off at this angle. You with me?
Yeah, so how do you figure that out?
Wonderful. That's what we got to figure out. So actually, let me turn my camera to get some of the whiteboard again, or some of the chalkboard again. And I'll scribble here for a second. And redraw this picture. So I'm going to redraw these two vectors roughly. So here's V2. And here's A2. And my picture is going to lie. Don't think too much about my picture.
Okay.
And put in a coordinate system really quick so that we can make some sense out of these things. You with me?
Okay.
So I need to create a right triangle right here, roughly. Not sure where exactly we can do it. Create some right angle right here. And then this component will be my acceleration in the same direction as my velocity vector. And this component will be perpendicular to my velocity vector. I need to take this acceleration vector and split it into these two components, which are not its x component and y component.
Okay.
Does that make sense?
Yeah.
So if I'm going to do that, I need to know this angle. So I need to be able to find theta. And if I'm going to find theta, I'm also going to need to know this angle, alpha. So we got to start finding some angles. You with me?
Okay.
So let me re-clean up this picture a little bit one more time. Now that you have a notion of what we're doing. And we'll start finding some angles. So here's V2. And here's A2. Okay, so let's start by figuring out this angle. Or we can figure out this angle if we want. We could do this whole angle for our velocity, and then we could find the accelerations angle, find the difference, and that will give me the angle in between. Okay, you with me?
Yeah.
So I'll call the outer angle theta, and the inner angle, this angle right here, we'll call alpha. And then the angle that we're interested in, this one, we'll call phi. So I know that phi is equal to theta minus alpha. With me?
Yeah.
How come we need to do that?
Because I need to take this acceleration and split it up. Let me redraw this picture one more time, reorienting my vectors. Here's V2. I'm just turning it. So here's my acceleration. I need to find the component of my acceleration in the same direction as my velocity, and the component of my acceleration perpendicular to my velocity. If I know this angle, which we're calling phi, then this distance right here, so if this is A2, right here is just A2, the magnitude of that vector, this distance right here then is a2 cosine of phi, and this is a2 sine of phi. So once I have phi, I can figure out these values.
I see.
Make sense? And ultimately, these are the two values we're looking for. So let's figure out really quick theta. Theta was the angle for my velocity vector. Theta is the whole angle from here to here. You with me?
Yeah.
Yeah.
Okay, so that angle is going to be, how am I going to get that? I know that theta is going to equal the arctangent, so tan inverse, of, what's my rise for V2?
That's
13 tenths. And what's my run?
-1.
But 1, since we're measuring our angle from right here.
Why isn't it -1?
Because we're not calculating the angle over here.
No, wouldn't it be possible?
We're calculating the slope. Look, I'm drawing that vector, redraw that vector right here. I'm calculating this angle,
Okay.
which uses both things positive since I'm measuring my angle from here.
But that
I'm
isn't
measuring
what
the
it is.
angle from right here. So I'm treating this like it's now my positive direction for my angle. Look, think
still lost.
intuitively about this and stop thinking about the numbers. Just think about physically what's going on.
Okay.
You're trying to figure out the slope of this thing, right? The angle gives you the slope of a vector.
Yeah.
The slope of the vector there. Now this angle should be the exact same as this angle. Doesn't matter the direction.
So why wouldn't the other side also be positive?
If I plug in a positive value, it's going to be using this angle. If I plug in a negative value, it's going to be giving me this angle. Because now, this angle is the angle for a vector that goes back 1. This angle is the angle for a vector going forward 1, because it's the same as this angle.
Okay.
Doesn't matter where I draw
That
the
makes
angle.
sense.
So redraw your angle, however it makes it click in your head, because ultimately the slope's the same.
Yeah.
Okay. So over 1, not over negative 1.
Okay.
Otherwise, it would give you a negative angle pointing down that lines up with this angle. That's what it would give you. Now, you could get the negative angle and then just flip the sign if you want. But, okay, so there it is. So what's our actual angle now? We go arctangent of 13 divided by 10, which is 52.43 degrees. Roughly 52.4 degrees. But that was for theta. Our alpha, how are we going to get our alpha? Same way, that's going to be the arctangent of, for alpha, it's going to be 3/10 divided by 2, or 3/5.
Okay.
Again, because we're measuring the angle from right here, not from way over here.
Yeah.
Okay, so when we take the arctangent of 3/5, what do we get? We get roughly 30.1 degrees. And so, and it kind of makes sense with our picture. Makes more sense when we look at this picture. This one's a bit more accurate than what we have up there. And so now we can find phi. Phi then, the angle between them, is going to be that minus that is going to be roughly 21.5 degrees. Good?
Yeah.
And now I can figure out what these values are. This is the magnitude of my vector parallel. This is the magnitude of my vector perpendicular.
Okay.
Oh, last thing I need is to actually get A up here. So let's figure that one out real quick. What is A sub 2? That's going to be the magnitude of this vector, the length of it.
How do you find magnitude again?
We use root
Pythagorean
square.
theorem. X squared plus y squared, square rooted.
Okay. That's right.
Okay. What'd you say? Oh, sorry. Where'd you say something? So that comes out to 0.583. So this is 0.583 meters per second squared. Now we'll figure out parallel to it. So I just write down this exact equation for the component parallel to it. Oh, parallel to is this one. So A2 times the cosine of phi is equal to 0.543 meters per second squared, and the component perpendicular to it, exact same equation, we just replace the cosine with a sine. And we get 0.213. So at that exact instant in time, the Mars rover is speeding up by half a meter every second, roughly.
Every second or every second squared?
It's speeding up, its velocity is increasing by half a meter every second.
Oh, I see.
Okay, there you go. Because the velocity is already meters per second.
Yep.
So it's meters per second. Good. Okay, and that kind of finishes that somewhat convoluted example. It's like 4 examples spread out throughout the book. I put them all into one.
Okay.
Good?
Yeah, I think so.
You can do that ease now? All right. Let's try and get my whole whiteboard. I think I got it. Okay. So now moving on to actual projectile motion. Throwing a projectile. Okay. 3 key things to keep in mind when I'm throwing a projectile through the air. Number 1, even though we live in a 3-dimensional space, when I throw this marker through the air, there's some vertical plane that the marker is following, right? The marker didn't go any that way or any that way. It just went that way and up and down, so it's traveling in this exact plane right here.
Can't you make it go this way or that way?
Not if we ignore air resistance.
Oh, okay.
Because you think like a curved ball in baseball, that has to do with the fact that they spin the baseball, so it spins on the air and causes it to follow more strange paths. So for projectile motion, we're assuming you're throwing these things in a vacuum.
Okay.
And so it's going to reduce it to a 2-dimensional problem for us, which is nice. We don't want to work in 3 dimensions if we don't have to. Second thing I want you to think about. When I throw this marker through the air, first off, so now we'll just think about in the x-y direction. When I throw that marker through the air, what's its acceleration in the y direction?
Acceleration in the y direction?
Yeah. Does it have any acceleration in the y direction?
Gravity.
No.
Gravity. It's constantly slowing down in the y direction. When I throw this marker, it starts out with a positive velocity up. And it's slowing down, slowing down, slowing down, slowing down, slowing down, stops. And now its velocity is becoming more and more and more negative. The velocity is always getting smaller when you think about more negative as smaller.
Okay.
So it has to have an acceleration in the y direction. Gravity is pulling it down.
Is that just a constant?
It's a constant, 9.8 meters per second squared.
Okay.
But it is accelerating downwards.
Would,
Its velocity in the y direction is changing.
would it be negative 9.8 then?
If we call that down negative. You can call down positive if you want.
Oh.
And we showed that
yeah,
last time.
We did. Okay.
Doesn't matter how you set up your coordinate system, physics doesn't care. This marker doesn't care what you call up or down. It's still going to follow down the trajectory it follows.
That makes sense.
Doesn't care what you call x naught, what you call y naught, what your coordinate system is. It's going to follow the path it's going to follow.
Okay.
Okay, next thing I want you to think about is its velocity or its acceleration in the x direction. So just in the x direction, as I throw it through the air, is it slowing down or speeding up in the x direction?
Slowing down or speeding up?
Or is it staying the same? Think about it, speed in the x direction. What's happening?
It speeds up, and then it
Well,
doesn't
it's
stay
air
the same.
resistance.
Ignoring air resistance.
And it just goes.
It stays the same. Right? Once it's going through the air, what's going to change its velocity in the x direction? Nothing's pushing it that way, nothing's pulling it that way.
So nothing.
So nothing. So the last key factor is to, when we think about its acceleration now in projectile motion, the acceleration vector, in the x direction it's always 0. In the y direction, if we call up positive, the y direction is always negative g. Does that make intuitive sense?
Yeah, that does.
Good?
Yeah.
Okay. So now, using our kinematic equations over there, those 4 equations, rewriting them really quick in the x and y direction here, using the fact that in one case my acceleration is a constant negative g, and in the other case my acceleration is a constant 0. And they only wrote 2 of them. So this is x is equal to x naught plus v naught t plus 1/2 at squared.
But that's
I see.
But a0. This is v is equal to v naught plus at, the a0 in the x direction. Then in the y direction, we're just rewriting those same equations, but this time we're replacing our a with negative g.
Okay.
Make sense?
Yeah.
I hate chalk. Alright. So the 4 equations I have written on the board right here, these all make perfect sense. No questions about where they're coming from?
No.
You still thinking about it?
That makes sense.
Okay, we're good?
Yeah.
Okay, so now we're going to think about projectile motion. We're going to think about throwing some projectile, starting at some point O, just for origin, and it's going to go up, reach some max height of P, and then come back and land on the ground at some point S. It's going to have traveled some distance D, and it's going to have gone some height H.
Okay.
And we're going to find a bunch of those values. So first thing I want to do is I want to find y in terms of x. I want to come up with the equation for this line the way that you're used to talking about equations of lines. So that if we think about this as a y-axis, y-axis, this is the x-axis, I want to come up with the equation such that for any x you can plug it in and it will spit out a y.
Yeah.
That's the first thing I'm going to do. So I'm going to express y in terms of x. Well, sorry, before we do that, let's rewrite these equations really quick with our given information. That's the first thing I should do. So first off, set the physical scenario. What's happening? I'm taking a ball and I'm chucking it with some initial velocity v naught at some angle alpha.
Okay.
And it's going up in the air, landing. We're going to ask these questions. Now, first thing we need to do really quick is figure out what's my velocity in the y direction and what's my velocity in the x direction.
How do you do that?
You know my velocity, you know my initial velocity,
So you just got it.
so you need to figure out my initial velocity in the y direction and my initial velocity in the x direction. How do you do that?
Make a triangle.
You make a right triangle. Use your trig functions. The exact same thing we did right here,
Oh, just with velocity.
just with velocity. Okay, so rewriting this equation now, I'm going to rewrite this equation with my picture. So these are general equations. So now I'm going to write the equations I care about for this particular picture. You with me?
Mm-hmm.
So my equation for x, we have x is equal to x naught, I'm just going to start at the origin, so that's 0, plus what's my initial velocity in the x direction?
Your initial velocity in the x direction.
Yes, so if you only know v naught, how do I figure out v naught x? If I know v naught and alpha, how do I figure out v naught x?
You gotta find
Cosine.
Cosine. So it's just v naught, the magnitude now, times cosine of alpha. Notice that we don't have to use vectors when we're talking about in one dimension.
Yeah.
Or in one dimension.
We're talking about just in the x dimension now.
Okay. Gotcha.
So in the x direction, here's my x point at any time. Well, that's just the velocity. Now I need to multiply it by time. So rewrote this equation. Right there for the case that we care about. Okay, good? All right. Now I'm going to rewrite this equation. That v in the x direction is equal to v naught times cosine alpha times t.
Times t.
Thank you.
Okay.
And notice, our velocity in the x direction doesn't change. Whatever it was initially is what it always is, throughout the whole flight of the marker. Our speed in the x direction, if we were going that way 1 meter per second, keeps going that way 1 meter per second until it hits the ground. Make sense?
Is speed parallel?
Right now we're talking about in the x direction. We're talking about how this thing moves just in the x direction.
Yeah, I'm saying is the x direction the speed, or is it the direction?
It has a speed in the x direction and it has a speed in the y direction. Look, when I throw this marker, did it move in the x direction?
Yeah.
So it has velocity in the x direction. Did it move in the y direction?
Yeah.
So it has velocity in the y direction.
But there's direction and then there's speed.
Well, we can talk about just its, we could do what we did here and have its position vector and talk about its position at every instant in time.
Okay.
Or we can just talk about its x position at any instant in time and its y position at any instant in time. And if you want to know its actual position at any instant in time, you take its x and its y and plot it. There it is. That's what these vectors do. It breaks up into, here's our x position, here's our y position. It's just bundling them together in one.
Oh, so we're trying to find that vector?
No, we're going to try and find how high this thing goes, and how far it goes, and how long it's in the air.
How long it's in the air. How do you find how long it is in the air?
We'll do all these things. One step at a time.
Okay.
Let's convert the equations and make sure we understand the conversion of the equations.
Okay.
Okay, one step. So this equation right here, this gives me my x coordinate at any time.
Okay.
If I know the initial velocity is 10 meters per second, and I know that alpha is 60 degrees, maybe just write out some numbers really quick to help you. So if I know that, however I throw this marker at an initial speed of 10 meters per second, so that's 10. And I know I throw it at an angle of 60 degrees. If that's 60, cosine of 60 is 1/2. Then in 3 seconds, how far has the marker gone? 15 meters.
Okay.
So in 3 seconds, it's going to be over here at 15 meters away
I see.
in the x direction. Okay.
In the x direction. You don't know about the y.
Yeah, we didn't figure out how high it is. We just knew how far in the x direction it had gone.
I see.
Okay. Similarly, this gives you its speed
In the
at
x
any
direction.
time in the x direction, which is always just this. It's constant. The speed in the x direction doesn't change.
Oh, so in your example, that would just be 5.
I don't remember what I wrote. No, it would be, yes, 5. You're right.
Okay. 5 meters per second. Right?
5 meters per second.
Okay.
Yes. Because now it's not a vector anymore. It's just a quantity.
Yeah.
That's why we reduce it to one dimension, so we don't have to work with the vectors.
So how would 3 dimensions look for this then?
You'd break it up into its x, its y, and its z. And your x would still look like this.
Okay, I see how that works.
Okay, so there's our equations for the x direction. Now let's start in the y direction. We have y is equal to, what's y naught?
0?
0.
Yeah, okay. Yeah, 0.
What's our initial velocity in the y direction? V naught sine of alpha,
Okay.
Yeah.
right? So V naught sine of alpha times t minus 1/2 gt squared.
Okay.
Good?
Yeah.
And then finally, our velocity in the y direction is going to be equal to our initial velocity in the y direction minus g times t. And this is assuming we call this way positive. Up positive.
Gotcha.
Good? Okay.
How do you find the max of that?
One step at a time. First, we're going to express y in terms of x. Then we'll find its max height. Then we'll find its max, the distance that it goes before histogram. We'll find all these things. Okay, so first off, I want y now in terms of x. I want the equation so that if you find the x, you can also get the y. You with me?
Yeah, how do you do that though?
So let's do that. So here's my equation for y, right?
Mm-hmm.
And so I need to replace these t's with something that has x's in them. So I'll come over here and solve for t. So I know from this equation, because the time's the same in both dimensions, time's time, right?
Yeah.
Yeah.
Okay, so I know that from the first equation, time is equal to x over v naught times cosine of alpha, right?
Yeah.
Yes.
So now I know that y is equal to v naught. Maybe I can write this all in one go and you'll just see it. So then I know that y is equal to v naught sine of alpha times t. You with me?
Mm-hmm.
V naught's going to cancel out with v naught.
So it's
Sine of alpha over cosine of alpha is tangent of alpha.
Yeah.
times alpha or times x.
And then times x.
Okay.
Perfect. Now,
The other
minus 1/2. I need to square this thing, so really quick, let's write out what t squared is. T squared is x squared over v naught squared times cosine squared of alpha, right?
Yes.
Okay, so when we plug in t squared here, am I doing this right? Gotta be doing it right. We didn't need to write that. I thought something else was going to happen. So minus 1/2, we're going to have g over v naught squared times cosine squared of alpha, all times x squared.
Yep.
You follow that?
Mm-hmm.
Now, the only important thing to know from this equation, it's kind of an empty equation, but the important thing to know is we already know what alpha is. That's one of our givens. So tangent of alpha right here, that's just a constant.
Okay.
And then this whole thing is also just a constant. So we have a y is equal to a constant times x. You can think about that as plus a constant times x squared. What are equations that have that structure? What type of equation is this? If you know y is equal to a times x, where a is just some constant, plus b times x squared, what do you know about y?
It's a parabola.
It's a parabola.
Okay.
Don't be so flippant with that k. That's some very useful information. Every projectile that you throw through the air, if you ignore air resistance, follows out the path of a parabola.
No matter what.
That's what we just showed.
Wait.
Ignoring air resistance,
Okay.
every projectile you throw through the air follows the path of a parabola.
So it always reaches the same height. I guess that makes sense. Yep. Okay. Yep. Okay.
Good? Okay, so that's the first major takeaway. All parabolic motion, all projectile motion is parabolic.
Yeah.
Follows a parabola. Okay, so now let's think about the height, p, the max height. Now what do we know about when this object reaches its max height? Is there any information there?
Velocity 0.
The velocity in the y direction is 0.
Yeah.
Perfect. So I know that the velocity in the y direction at point P is equal to 0. Right?
Okay.
So, where are we? So I know that this equation, this equation right here, this is 0. This is equal to 0 at P.
At P. Okay.
So in other words, I know that 0 is equal to v naught times sine of alpha. Those are just givens. minus g times the time it takes to get to point P.
Yeah.
So that gives me that the time it takes to get to point P is equal to, I'm going to move this to the other side and then divide both sides by g.
Negative g.
G, because I moved it to the other side.
Oh, okay.
Good? So is equal to v naught times sine of alpha all over g. That's the time it takes to get to P, right?
Okay.
So then the height at P, which is our max height, the height at P, y sub P, is equal to, looking at this one now, v naught sine of alpha times t, but this is going to be our t, right?
Okay.
So we're going to get v naught squared times sine of alpha squared over g. You follow that? Just plugging that in for time right here.
Yeah.
Minus 1/2 g times this thing squared.
Okay.
So when we square that thing, we're going to get v naught squared times sine of alpha squared all over g squared. You with me?
And one of your g's cancel out.
One of your g's cancels out, so get rid of that and get rid of this. And so now you have one of these minus 1/2 of these is equal to 1/2 of these,
Yeah.
right?
Mhm.
So we're left with v naught squared times sine squared of alpha all over 2g. We do that right? Yes. Okay, so there's your max height. If you know the initial velocity and you know the angle it's thrown at, here's the max height that that thing will reach.
So it doesn't even give us the angle. We don't need to find out the angle, do we?
No, the angle needs to be given to you. You need to know the initial velocity. You need to know how fast I throw this marker and what angle I throw this marker at. That drastically changes the max height it reaches. If I throw it at 1 meter per second straight up, that's going to get a lot higher than if I throw it at 1 meter per second straight out.
Yeah. Okay.
So the angle definitely matters. So notice what this says. This says that the max height, what makes it get higher? It gets higher if A, you increase your velocity, the speed you throw it with. If you increase the speed you throw it with, that's going to make it get higher. Furthermore, how do you max out sine? Where is sine the biggest? Where does sine have its max value? What angle gives you a max value for sine? What's the biggest number my sine function can ever spit out? What's the biggest sine of theta can ever be?
1.
1. When is it 1?
Straight up.
At 90 degrees. So this is also saying if you want to make this number as big as possible, throw it at 90 degrees. Which is also obvious to us. If I throw something straight up, it's going to go higher than if I throw it with the same speed on some angle.
Okay.
Does that make sense? I just want you to have some physical intuition into what this equation is saying. Don't look at it as just numbers on a board. Make it make sense in your head. So increasing velocity increases the highest that this thing goes, which is equal to h. Sorry, let's put h there. H is how high it goes. Okay, how high does it go? Or what makes it go higher? Increasing the velocity increases the height. Making the angle closer to 90 degrees increases the height. Furthermore, if you decrease gravity, if you make the denominator smaller, you'd also increase height. So if I throw this marker the exact same way on the moon where there's less gravity, it would also go higher.
Yeah.
And that's what the equation is telling us. I'm just reading out what this equation is telling us.
Okay.
And it better make perfect physical sense why those numbers are the way that they are.
Yeah.
Good?
I think so.
Okay. Let me give you an example of something that should disturb you. It should have been very disturbing if after you did all your math, you instead, well, that's equal to h. It should have been disturbing to you. What if he came out with something like v naught squared times cosine squared of alpha over 2g? If you're just looking at the math, if you're just looking at numbers, you wouldn't think much of that. You'd say, okay, there's a formula. Think about how this formula makes no sense. This formula says you get your max height. If I said height was equal to this, you should be screaming that makes no sense. Because it's saying, if we had cosine here, when is cosine max? At 0 degrees. This is saying you reach your max height at 0 degrees.
Yeah.
And when's cosine 0? At 90 degrees. That would be saying if you throw the marker straight up, you get no height. If this equation were true. Obviously it's not.
Yeah. Okay.
So if you see something like this, that's a bunch of nonsense. Now, prior to this class, if you had just walked in and I said, here's your equation for height, you might have said, oh, okay, and gone on your merry way. Anytime you need to get the height, you go look up your equation, and it makes no sense. Make it make sense. Otherwise, you're going to have a big storm of equations that you have to memorize with no ways to do even a sanity check if you're remembering the right equation for the circumstance you're talking about. I'm trying to help you not turn this class into memorizing a whole bunch of equations, but getting physical intuition for the mathematics. Look at the math and get the physical intuition as to what exactly that math is telling you. That's what's crucial. Make sense?
Yeah.
Okay, so now let's find how far this marker goes. So like, if I were to give you the initial velocity at any angle, you can tell me exactly how far it would go. Wouldn't that be nice?
Is that assuming it's all flat?
Yeah, it's assuming it starts and ends at the same height.
Okay.
Good?
Yeah.
Okay. So, first thing I want to know is how long is it going to take that marker to land? And then once I have the time, I can figure out the x position at that time, which is how far we went. You with me?
Mm-hmm.
So I know how long it took for it to reach the point P. I already have that time figured out. That's right here.
Yeah.
What's the time it takes for it to go all the way and reach the ground? You could take this equation right here and solve for when y is equal to 0.
Okay.
And get your answer that way. Or you could use the insight that we got from this equation, namely that this thing is a parabola, know that this thing is symmetric,
Mm-hmm.
and so know that the time it takes for it to go from here to here is equal to the time it takes for it to go from here to here.
So it's just 2.
So the time it takes for it to go from here to here is just 2. So the time it takes to reach S is equal to 2 times the time it took to reach P is equal to 2 times V naught times sine of alpha all over G. You with me?
Mm-hmm.
Okay, so now let's figure out what D is, this distance. So the distance it goes D is equal to, or its final x position, however you want to think about it,
Yeah.
is equal to our velocity in the x direction times how long it's been traveling with that velocity, which is right here.
Wouldn't that all equal 0 then?
No. So let me simplify it again. So D then is equal to, we have a 2 V naught squared, 2 times V naught squared, times sine of alpha. Let me write the V naught squared first, because maybe you'll see it, maybe you won't, I don't know. So we have V naught squared times 2 times sine of alpha times cosine of alpha all over G.
Isn't 2 times sine of alpha times cosine of alpha just 1?
No, but it is something. I was almost impressed. I thought you were going to say it. So D is equal to V naught squared times sine of 2 alpha all over G.
Oh.
2 sine of alpha cosine of alpha is sine of 2 alpha. Okay, so now let's make intuitive sense out of this equation. Let's make sure that this makes physical sense.
Okay.
This says that the max distance we go gets bigger if we increase the velocity we throw the marker with.
Yeah.
Makes perfect sense, right?
Yeah.
What angle gives me the max distance?
Max distance?
Yes.
the same as your y.
No, because that's straight up and that doesn't go anywhere.
Is it sine of 2 alpha? I think it's sine squared of 2 alpha. Sorry. But it doesn't change my question.
What?
I think 2 sine of alpha cosine of alpha is equal to sine squared of 2 alpha. I think that's the trig identity. Trig identity. 2 times sine of alpha times cosine of alpha is equal to sine squared of 2 alpha.
Okay.
That's the substitution. Anyways,
It's just sine 2 of alpha.
huh?
It's just sine 2 of alpha, not squared.
It's not squared?
So my thing's saying. Sine 2 of theta is equal to 2 times sine of theta times 2.
Oh. It actually makes perfect sense. It's not squared. Okay. Because the sine of alpha plus beta is sine of alpha cosine of beta plus sine of beta cosine of alpha. Okay. I just realized how to prove it. Thank you. You're right. It's not squared. Good job. Okay. Anyways, coming back to this equation, what angle alpha maximizes my distance?
45.
45. How'd you do that? Did you just think about what made sense, or did you look at the math?
Well, 45 times 2.
Okay, perfect. So you thought about what made sense, and you just made the connection. 45 times 2 is 90, maximizes my sine.
Yeah.
And that's the 2 connections I want you to make. 45, what maximizes my sine? 45-degree angles. Just intuitively, if I want to throw this marker as far as I can, ignoring air resistance, what angle should I throw it at? 45 degrees.
To get your max distance.
To get my max distance. To get my max height, I throw it straight up.
Okay.
What about to get my max time in the air? Which one keeps the ball in the air the longest?
Both of them together.
You say just straight up? I don't know what you mean by both of them together. You're saying 45?
Yeah, 45.
You're saying 45, you're saying
Straight up.
you're going with straight up?
What if you fall way faster with straight up?
If you throw it straight up, you fall down the exact same fast as you would. No, you don't fall faster. The answer is yes, straight up.
What?
The answer is straight up.
Okay.
Ignore the problem in the x direction. What happens in the y direction? It goes up and falls. Right? The fact that it has some x velocity doesn't change how fast it goes up or how fast it falls. An object doesn't fall slower because I throw it that way.
It just doesn't go higher.
Do we need to see an example of this?
Sure.
Let's see if I can do this. I need to try and throw this just straight out, and I need to try and drop this. I don't know if I can do this. I might have thrown that one up a little. Here's how to do it.
We'll just throw one up in the air.
Roll one off the table fast, and roll one off the table slow, or then drop this right as this one's rolling off the edge. Right? Because it'll have some x velocity.
Yeah.
Yeah.
So if I roll that off the edge, turn up. Don't have great tools to test it. But no, having an x velocity doesn't change how fast gravity pulls you down. You can't like outrun gravity.
Okay.
So gravity pulls you down the same, doesn't matter if you're going this way or not. What happens in the y direction does not care about what's going on in the x direction.
Well, the way I was thinking about it is, what about acceleration?
There is no acceleration in the x direction. It's all in the y direction.
Yeah, I'm saying if you threw it really high in the y direction, it would accelerate faster to the ground.
No, it's always accelerating at the same rate in the y direction.
Oh, that's right.
The acceleration in the y direction is a constant.
Okay.
Maybe we can just like demo this just the more straightforward way. If I throw this straight up and it's time in the air, versus if I throw it like that, harder still. No good demo. Times we're talking about are too small. But intuitively it should make sense.
Yeah.
What's going on in the y direction does not care about what's going on in the x direction. In other words, if I were to take a ball and throw one ball straight up like this, and I were to take another ball, and I were to throw that ball like this, those both send the spend the exact same amount of time in the air because they both went the exact same height. If you just look at it in the y direction, what happened in both those cases? The ball went up and came back down. The ball went up and came back down. The mathematics in the y direction is identical in both these cases. It's only in the x direction that it changes.
That's funky.
Starting to get a little bit of understanding about how throwing objects work. How falling objects work.
Yeah.
Isn't it amazing how long you live in a universe without understanding something as simple as that?
That's not very.
Crazy. Okay, so there we go, projectile motion, and I calculated all the most interesting things you're most likely going to have to calculate in your problems. Your problems are going to ask you to do things like calculate the x velocity at a certain time, we got an equation for that, or the y velocity at a certain time, we got an equation for that, or the max height the object reaches, you got an equation for that, or the max distance the object goes, you got an equation for that. Now you don't need to memorize those equations, you can come up with the stuff as you go. I just wanted to walk you through it once in case you get stuck, then you have something to fall back on. And hopefully everything now makes intuitive sense.
Okay.
Good?
I think so.
Okay. So now we've got to go on a tangent away from the book because I hate how the book does this next part. And we'll kind of go back to where we started in calculus. If you remember that far back. Remember our first lecture in calculus?
Just trig.
Some basic trig. So we'll go back to some basic trig and add a little bit to it. Some trig stuff that you haven't seen before, but it's not complicated. So first off, going back to our definition of pi. What is the definition of pi?
No.
I'm going to throw something at you. What's the definition of pi? If I have some circle with radius r,
It's half the circle.
what is pi? How do you calculate pi? Okay. If I have some circle, repeat lecture 1. If I have some circle,
Okay.
what's the distance all the way around the circle called?
The circumference.
Circumference, right?
Yep.
And then what's the distance across the circle called from here to here?
Diameter.
Diameter. So definition of pi is circumference over diameter. So it's definition.
Oh.
Okay. So when you say pi is approximately 3.14, what does that mean? That means if I have a circle that's 10 meters across, its circumference is roughly 31.4 meters.
Yeah.
Pi is a ratio between circumference and diameter. That's all it is. Good?
Yeah.
Okay. So then we can get, from that, we can get an equation for circumference. What's circumference? 2 pi r. Right?
Yeah.
So if I tell you that the radius of the circle is 5 meters, what's my circumference roughly?
31.4.
31.4 meters. Right? Okay. So notice that no matter the size of the circle, doesn't matter how big or small the circle is, the circumference, the distance to get all the way around the circle is always 2 pi times its radius. Right?
Mm-hmm.
And so 2 pi radiuses get you around the circle.
Okay.
1 radius gets you roughly this far on the circle, we'll say.
Oh yeah.
1 radius, 2 radiuses, 3 radiuses, 3.14159 radiuses, etc. 6 radiuses get you about right there, and 2 pi radiuses get you all the way around the circle. And that's true no matter the size of the circle, big or small.
Yeah.
1 radius always marks off the same portion of the circle. We call the portion of the circle that 1 radius marks off 1 radian.
Yeah.
It's the angle marked off by 1 radius.
That's right.
Yes. And we've been working with radians a lot, right? How many radians are in a circle?
How many radians?
How many radians?
Just 12.
No.
2.
2. No. There's 2 pi.
2 pi! Holy cow! How many radians are in a circle? 2 pi. How many radiuses does it take to go all the way around the circle? 2 pi.
Okay.
What's 90 degrees in radians?
In radians?
Yes. What has happened to you guys? What is this angle in terms of radians?
Oh, 1/4.
What?
1/4.
Pi.
In radians.
So, pi force.
Yeah.
Do you guys not remember your unit circle at all?
It's coming back to me now.
Holy cow. Okay. We gotta do way more review than I thought. Thought you guys would be snapped in and we'd be halfway done by now. We can't get past a radian. Okay. Unit circle. We'll mark off some points. We'll mark off some angles.
Okay.
Okay. By definition, a radian, if this is one radius, so here's r right here, right? If the distance from here to here is r, then this angle is, we'll put that r down there, 1 radian. You with me?
Okay.
Yeah.
So, how many radiuses does it take me to get halfway around the circle?
Pi.
Pi radiuses. This arc length from here all the way to here is pi radiuses. So this angle is pi radians.
Pi radians. Okay.
Yes. And to go all the way around the circle is 2 pi radians.
Okay.
You with me so far?
Yeah.
So now let's do some quick conversions between degrees and radians. If I have 360 degrees, what is that in radians?
2 pi.
2 pi radians. Oops. If I have 180 degrees, what is it in radians?
Just 1 pi.
Pi. 90 degrees.
Pi half.
Oh, pi halves. Okay.
60 degrees.
Pi third.
Pi thirds. 30 degrees.
Pi 6.
Pi 6. 45 degrees.
Pi quarters.
Pi fourths. Those things we used all last semester. Radians. Angle measurements.
Okay.
Okay. We back?
Yeah.
Yep.
You're gonna need to make you guys do a unit circle again.
We just need to take 3.
Okay. So now that we got radians back in our brain,
Yeah.
I'm going to use S now to talk about the arc length. So if my angle in radians is 2 pi, so in other words, we're going all the way around the circle. If theta is 2 pi, we're going all the way around the circle. What's my arc length all the way around the circle?
2 pi r.
The circumference, 2 pi r.
Okay.
With me so far?
Mm-hmm.
Okay. Now, if theta were just pi halves, so if we were talking about a 90 degree angle, what would my arc length be?
It would just be pi half r.
Pi halves r,
Radius.
right?
Yeah, I see it.
Let's get a more concrete example really quick. Let's say that you walk around a circle. So let's say we got a circle now with a with a radius of 10 meters. And let's say that you walk 135 degrees around that circle. Question, how far did you walk? So you're right here and you walk 135 degrees around the circle. How far did you walk?
3 pi quarters 10.
5 quarters 10.
30 pi over 4 meters. That's what you're saying, right?
Yeah.
Now how did you do that? You first took 135 degrees and converted that to radians. And so that's 3 pi fourths. And then you multiplied it by the radius. And that gave you the distance.
Oh, I see.
And so that's why having 8 degrees is so annoying. And why we love radians so much.
Okay.
Because it's way easier to work with when we're trying to get arc lengths. Which is something we do a lot. And we're going to do a lot. So we like radians, not radiuses. So in general then, how do I get the arc length if I know theta? If I know what theta is, how do I get the arc length?
Multiply theta by r.
You just multiply it by r. So if I have theta in terms of radians, just multiply it by r, that gives me my arc length.
Okay.
Good?
Yes.
Okay, so we got our first important point. Okay, so now just talking about circular motion for a second. Kind of ignore the arc length portion of it. We're going to talk about going in a circle, and we're going to talk about, rather than your x position, your velocity, and your acceleration, we're going to talk about the current angle you're at, how fast your angle's changing, and then your angular acceleration. So let's get notion for this really quick.
Okay.
So let's say you are right here and you're walking in a circle. Okay? So you start out right here at 0 degrees, and then you go up to right here at 90 degrees. So theta 1, or theta 0 is equal to 0, and theta 1 is equal to pi halves. You with me?
Yeah.
So your displacement then was
Pi half.
pi half radians. If you started at pi halves, and you went to pi, your displacement was
Pi half.
Radians.
pi half radians, right?
Why radians?
We're going to just measure our angles in terms of radians,
Okay.
because it's way better than degrees. That's like asking, why do we use meters instead of feet? Why not use feet? Because meters is better. It's
Okay.
easier to work with. Can you work with feet? Sure. Could you talk about all this in terms of degrees? Sure. We're going to talk about it in radians.
Okay.
Good?
Mm-hmm.
Okay. So now, imagine that you are walking around the circle. So here you are walking around the circle. And it takes you 4 seconds to go all the way around the circle.
Okay.
So then I ask, what is your angular speed equal to? Which we represent with omega. If it takes you 4 seconds to go 2 pi radians, then what's your angular speed? How many radians are you going per second?
Pi half radians.
You're going pi half radians per second.
Radians per second. Okay.
Radians per second. Rather than meters per second, just radians per second. You with me?
And when you get your radius,
Yeah.
you just plug that in over.
Well, we'll kind of ignore radius for a second, or not for a second. I just wanted to get comfortable with what omega is. So this
Omega is
omega
just a
comes up.
W.
That's not supposed to be a W. That's supposed to be a Greek letter omega. You know, it'll look like an omega in your book. Yeah, it looks like a W. Just more fancy W. Should be more curved like this if I really tried something more like that.
Really?
Omega. That made me wonder if I'm saying the right letter.
I thought omega looked different. I'll take your word for it.
I think that's right. Well, now you got me wondering. I think it's called omega. But Greek letter there, not just a W. Greek letter omega. And we use that to represent your angular speed. This isn't how many meters per second you're going. That depends on how big this circle is. Right?
Yeah.
If this is a really small circle, and you're going around it, and it takes you 4 seconds to go around it, you're going 2 pi radians per second. If this is a massive circle, and you're going around it in 4 seconds, you're still going pi half radians per second.
Okay.
So this doesn't give you your velocity, it just tells you your radians per second. That's what omega gives you.
Omega?
Omega.
Like alpha and omega?
Yes.
Okay.
Okay. So omega is your, so now let's just come to our table so that you see the similarities. So your change in theta, your displacement in theta, the change in your angle, is your final angle minus your initial angle in radians. Makes perfect sense, right?
Yeah.
Yeah.
Okay, omega then, we're saying is equal to your change in your angles with respect to time.
Yep.
It's how many radians per second you're going.
Okay.
And so if you want it precisely, omega is going to be the derivative of your angle with respect to time.
Yeah.
And then alpha, here, we call your angular acceleration. It is going to be your change in your angular speed with respect to time. And so it's going to be radians per second,
Okay.
or radians per second squared. And hopefully, it's already making intuitive sense to you. You're already seeing the parallels between this and just the motion you're used to. Motion you're used to this. Displacement in s, it's your final position minus your initial position in meters.
Yeah.
Right? And now we know how to calculate that displacement. That's your change in theta times r. Yes.
Okay. Yeah,
Right?
because the size of the...
This is radians multiplied by r gives you radiuses.
Okay.
Now, I want to talk for a second. Well, we'll finish filling out this table really quick and then have the discussion. Once again, velocity, the way that we normally talk about velocity, that's your displacement over time. Right?
Yeah.
That's how we talk about velocity. But now, how can you calculate your displacement? Your displacement is the same thing as the change in your angle over time. Or sorry. Delta S is the same thing as delta theta over r, right?
Mm-hmm.
And so delta S is delta theta over r. Delta theta over delta t is what omega is.
It's just omega times...
Let me write this one more line in here to probably did 2 steps too fast. So this is equal to delta theta times r over delta t, which is equal to omega times r.
Oh, I see it.
You see it now?
Mm-hmm.
So if you know your angular speed and you want your actual velocity in meters per second, you just multiply by the radius.
Yeah.
So going back to this example, so up here in this example, we know we were going pi half radians per second, right?
Okay.
Well, if our circumference, if the circle we're talking about has a radius of 4 meters, now what's your velocity equal to?
It's W times R. So, pi half times 4.
Pi half times 4, which is 2 pi meters per second.
Oh, I see. Okay.
You good?
Mm-hmm. Yeah.
Similarly with angular acceleration. If you know your angular acceleration, you can calculate your actual acceleration by just multiplying by r.
I see. Yeah.
And this is why we love radians. When you measure in radians, all these equations work. If you get your angular speed in radians, you just multiply by the radius and it gives you your velocity. If you have your angular acceleration in terms of radians, you just multiply by r and it gives you your actual acceleration.
Yeah.
Or your linear acceleration, we'll call it. Do these equations all make sense?
They do now, yeah.
Okay, now we got to make a point here. Because this came up last time and I wanted to put off until we had this conversation. I told you that the units that we always talk about, always measure in this class are meters, kilograms, and seconds. Or lengths, distances or lengths, times, and masses. Those are the 3 things we measure.
Yeah.
And one of you said, what about angles? Right? What about degrees or what about radians? What are the units for those? And I said that those have what we call dimensionless units.
Yes.
Now, why does a radian have a dimensionless unit? Let's make sense of that really quick.
Okay.
You with me?
Mm-hmm.
So notice from our equation right here, I can rewrite theta is equal to your arc length, s, divided by your radius. You with me?
Yep. Yeah.
Arc length is measured in terms of meters. Your radius is measured in terms of meters.
Yeah.
And so an angle is actually just a ratio of 2 lengths. And so the meters and the meters cancel out.
Oh, I see.
And so it doesn't have any dimension to it. So that's why we call it a dimensionless unit. So that's why when I take something like, I just wrote radians per second here to help you wrap your head around what we're talking about, right? Omega. But that's why when I take something like omega, which is radians per second, and I multiply it by a radius, which is some amount in meters, it comes out of velocity, which is meters per second. The radians are a dimensionless unit.
Okay.
It just helps us keep track of what kind of ratio we're talking about. Are we talking about a radian ratio, or are we talking about a degree ratio? So degrees and radians are dimensionless. They just help us keep track of what kind of ratio we're talking about. Does that make sense? Okay, so that's why in these equations, when I do something like omega times r is meters per second, or alpha times r is meters per second squared, or arc length, which is radians times meters, is just meters, and not meters radians, or something like that. Make sense? Mm-hmm. Okay. Last thing we got to talk about. Uniform circular motion now. Uniform circular motion. What do we mean by uniform circular motion? When we say uniform circular motion, we mean you are walking in a circle at the same speed. You never speed up, you never slow down. You're just going around a circle at a constant rate, whatever that rate is. Okay?
Yeah.
That's what we mean by uniform circular motion. So if you're traveling in oh, we didn't fill this out. Forgot to fill this out. So we'll come back to uniform circular motion here in 1 second. Let's fill this out really quickly. Your position at this point. What's your position at that point? What's your x and y coordinates at that point if you know that it's a circle of radius r and at angle theta? How do you calculate your x coordinate?
Cosine.
So what is it?
Cosine theta.
Is it just cosine theta?
R times cosine.
R cosine theta. So your x coordinate is r cosine theta. And this coordinate is r times sine theta.
Yeah.
Which if you were to draw a right angle, this distance right here is r cosine theta. And this distance right here is r times sine theta.
That's right.
Right?
Yeah.
That's how we get those numbers? Okay, so this gives me your position, your x and y coordinates at any angle. You with me?
Okay.
Okay, so now imagine, well, I guess we'll do some definitions and we'll come back to that conversation. So uniform circular motion. What do we mean by uniform circular motion? We mean you're traveling around with a constant velocity or with a constant omega.
So omega is constant, not
So-
your alpha.
Yeah, well, if your omega is constant, your alpha is 0. Because alpha is changing omega.
That's right.
So alpha is 0, omega is constant. So if omega is constant, then your velocity, v, is also constant. Because it's just omega times r. R is a constant, that's just the radius of your circle,
Oh.
times omega. So you're traveling around with constant speed. The direction is changing, but the speed is the same. This isn't just the speed. It's the magnitude of your velocity vector.
Okay.
You with me?
Mm-hmm.
Okay, so that's what we mean by uniform circular motion. Going around with constant omega, constant speed. Okay, now in uniform circular motion, there's two quantities that we're interested in. There's two things that we need to find. One of the things we're interested in is how long it takes you to go all the way around the circle. And we call that your period. So if you're going around the circle, if it takes you 5 seconds to go around the circle, then your period is 5 seconds. And we use capital T for period.
Okay.
Obviously.
Yeah, you'll get used to it. Like 30% of the letters we come across for this class, what they represent, you're like, why that letter? It's because the letter we wanted was already used in scenarios that often come up close with this.
Okay.
Anyways, so period is your period going around the circle. How long it takes you to get around the circle. And time is equal to distance divided by speed. 2 pi gets you all the way around the circle.
Yeah.
Okay.
Omega is your speed going around the circle. And so that will give you your period. For example, if I say you are traveling at a rate of pi 6 radians per second,
Mm-hmm.
what is your period?
1/3 pi. 5 thirds.
make sure it makes sense. How many seconds will it take you to go around the circle?
Okay.
You're going pi 6 every second.
It's just 12.
12?
That's,
No.
that was weird.
Well, it's just, isn't it 6 pi, 2 pi over 6 pi?
2
Right.
pi over pi 6.
Isn't pi 6 just?
Okay, let's think about this the most straightforward way that a preschooler would address this problem.
Okay.
Okay.
Here's your circle. Here's 1 pi 6. Here's 2 pi 6. Here's 3 pi 6. Here's 4 pi 6. Here's 5 pi 6. Here's 6 pi 6. I go 1 pi 6 in a second. That's how far I get in 1 second. 2 seconds. 3 seconds. 4 seconds. 5 seconds. 6 seconds. A period 6. Takes 6 seconds to get around the circle.
Okay.
If you're going pi 6 radians every second, how long does it take you to get around the circle?
6 seconds.
So what about the 2 pi?
Okay,
Okay.
we just went 2 pi. That's what we did. Look, you're saying, how long times pi 6 do I got to go to get 2 pi? Oh, I wrote pi 6 and I was thinking pi thirds. He's been right this whole time. 12 seconds.
That's what I thought.
Pi 6 is 30 degrees. Yep, that's my bad.
Okay, I'm lost.
He was right the whole time. Pi 6 looks like this. Go back to preschool method. Pi 6 is like this.
Oh.
1 pi 6, 2 pi 6, 3 pi 6, 4 pi 6, 5 pi 6, 6 pi 6,
Oh, I see.
7, 8, 9, 10, 11, 12. When you have 12, 6, you have 2 of them. And 2 pi gets us the whole circle. Okay, another straightforward way. I can't believe
Well, no, it makes sense, but what
you're
about
going
before
pi
we-
6 every second. How long until you go 2 pi?
12.
12 seconds.
Okay.
So t is the time it takes us to get all the way to 2 pi, by definition.
Okay.
So t is always equal to, another way we could have written that is t is equal to 2 pi over pi 6 in our example,
That's 12.
which is equal to 12 seconds.
Oh, I see. I see where they wrote. Okay.
So for any omega, plug it in there, and
It works.
it will give you the period.
Okay.
Okay, so that's a period. Now another definition we have is frequency. Frequency is 1 over the period. Period says how long does it take me to go around the circle. Frequency says how many times do we go around the circle in 1 second.
Okay.
Okay?
So I could use
So imagine that I go around the circle 5 times in 1 second. You with me?
Mm-hmm.
If I go around the circle 5 times in 1 second, what's my period?
1/5. Yeah.
So my period would be 1/5. And my frequency, if I'm going around it 5 times per second, is 5. You with me?
No, your frequency is 1/5.
No, that's my period. My period, if I go around the circle 5 times in 1 second, my period is 1/5 a second.
Oh.
Okay.
My frequency is 5.
Times per second.
Seconds inverse, 1 over seconds. Look at how it's defined. Frequency is 1 over a time.
Yeah.
Seconds inverse. Seconds inverse, we have a special name for that. We call it hertz.
Hertz.
Yes.
Okay.
How many
Hertz.
hertz?
Isn't a hertz like have to do with?
What? Does it have to do with frequency? Yes. Frequency is measured in hertz.
That's cool.
Connections. Yes, when you talk about frequency in electricity, we're talking about frequency.
Okay.
Yes.
Frequency is just circles? I'm confused.
You know those.
We're not going to get to electricity and magnetism today.
Okay.
So we're going to focus on, if you go around a circle, if you're going around a circle, your frequency is how many revolutions you complete per minute, or per second.
Percent.
Yes. So if you go around the circle 5 times in 1 second, you have a frequency of 5 hertz.
That's so.
You'll be making a lot of connections like that. Okay. So that was our definition for period and frequency. I think we got those.
Okay.
So now going back to talking about uniform circular motion. Uniform circular motion. So now you're just traveling in a circle. We'll use this picture here. You're just traveling around in a circle, right? And we'll call this now your position vector. R is going to be your position vector. It's going to give me your position at any time t. You with me?
Yeah.
Now, I know what your position is. Your position is r cosine of theta, r sine of theta. That's the position of a point, if it makes some angle theta, right?
Okay.
So if I know that my position vector is pointing out at some angle theta, then I know your x-coordinate is r cosine of theta, where r is the length of this vector, and r sine theta for your y-coordinate, right?
Okay.
So looking at this picture, you see how this vector makes perfect sense?
Yeah.
Yeah.
Okay, but I guess we didn't really make this equation make perfect sense yet. If omega is how many radians per second you're going, so if I'm going pi halves radians per second, and I do that for 4 seconds, what do I get?
2 pi.
2 pi. But it gives me an angle. So radians per second times some number of seconds gives me an angle. So theta is equal to omega times time. It's the same thing as rate times time equals distance.
Okay.
Your angular speed times your time gives you your angular distance.
Okay.
Does that make sense?
Yeah.
So you're traveling around in a circle, and your theta is going to change for every point on the circle wherever you are, right? It will always be this for whatever that theta is, but how do we figure out that theta? We take your angular speed and we multiply it by time. So at 0, you're right here.
Yeah.
And then after 1 second, depending on what your angular speed is, if your angular speed was pi halves, at 1 second you'd be right here, at 2 seconds here, at 3 seconds here, at 4 seconds here, 5 seconds here, etc. Right? So, rewriting this equation, since we know that theta can be written as omega times t, rewrote the exact same equation right here, replacing theta with omega t. Go ahead.
When you go all the way around the circle and back again, so if you want 5 pi halves, does it go more than 360 degrees?
Yes. You can go to 10 trillion degrees. Nothing wrong with that. Good? So the important part to wrap your head around is that this gives us our position at any time t on a circle.
Honest. Okay.
If we're going with, well, this is true for any time t on a circle, but we're also going to assume that omega is a constant, because we're talking about uniform circular motion. Omega is a constant.
Okay.
Does that
And so we're going to use that information now to figure out our velocity and our acceleration vectors.
Don't you have to know where you start in order to find out where you're going to be?
This tells me where I start. Plug in 0.
Oh, sorry.
So we're assuming you start there.
Yeah.
Good? Okay, so now what is our velocity vector? Equal to. Sorry. Hopefully you remember how to do this. R is a constant, omega is a constant, t is our only variable.
So you got to do the chain rule.
So what's the derivative?
Oh, the derivative,
Negative
it's
sine.
the, yeah, chain rule.
So we still have our r there. R times sine omega t times the derivative of the inside, which is
T.
Just t.
omega. T is our variable. Omega is our constant.
Oh, yeah.
What's the derivative of 9x with respect to x? 9 is the constant. It's not the variable. Okay, so now I'm going to rewrite this one more time. I'm going to write the exact same thing. I'm just going to write the omega first. So this is equal to the square root of negative omega times r times sine of omega t. You with me?
Yeah.
Square root.
Square root?
You said square root somewhere in there. And then didn't write it.
I have no clue why I said that.
Yeah.
Okay. Anyways, and then when we take the derivative of this, what do we get? we get omega times r times cosine omega t.
Yes.
You follow that?
Yeah.
Okay, so now I'm going to calculate our acceleration vector. Our acceleration vector then is equal to, derivative of sine is just cosine, right?
Yes.
And then we'll just multiply by another omega. So it's going to be negative omega squared times r cosine omega t, comma, negative omega squared times r times sine omega t. You follow me on that?
Yeah.
Yes, sir.
Okay, now I'm going to pull the omega squared out of the vector. Omega is just a real number, right?
Okay.
So this is the same thing as omega squared, and then we scale up this vector by omega squared, and we have, maybe I'll also factor out the negative, omega squared, and we'll factor out negative 1 as well. And so we have r cosine omega t, comma, r sine omega t.
Isn't that just your position?
Wonderful! So our acceleration vector is equal to omega squared times the negative of our position vector.
What the? Okay.
Wonderful, beautiful symmetry. Now, what does that mean?
Yeah.
So think about at a point, like right here. Get rid of this other noise for a second. Think about at a point right here. What is my acceleration vector at that point? What do we know about it?
Here's
What direction does it point? Here's my position vector. My position vector points from the origin, and it points out to that point right there, right? Notice my acceleration vector is my position vector,
Just pointing the opposite.
scaled by omega squared, pointing in the opposite direction. So my acceleration is pointing this way. This way is my acceleration vector at that point. It's pointing radially inwards. It's pointing towards the origin. It's pointing in the exact opposite of my radius.
Is it always pointing towards the origin?
Yes, because the radius is always pointing away from the origin.
Okay.
And it's always pointing in the opposite direction. So in uniform circular motion, if you're traveling around, so your velocity here is that way. Remember, velocity is always tangent. Or your velocity is that way. Or your velocity is that way. Wherever you are, your acceleration is always pointing exactly towards the middle of the circle.
So you're accelerating towards the center of the circle?
You're always accelerating towards the center of the circle because you're not speeding up. So all your acceleration is just going into turning view. And so if you're going around a circle, you're always just making a left-hand turn. It's an infinite left-hand turn.
Yeah. Okay.
Okay.
Right? Make sense?
Yeah, that does.
Okay. So your acceleration, then, here's your acceleration vector. If we just want the magnitude of it, so just A, not the actual vector now.
Okay.
So then A is going to be equal to just the magnitude of this vector, which is just r times this. So it's just going to be omega squared times r, where r now is just the length of your radius.
How about the negative?
The magnitude of negative r is still just r,
Because it's okay. Yep.
the magnitude of that vector. You don't have negative distances. Anytime we talk about magnitudes, it's always a positive number.
Yeah.
Does that make sense?
Squared. Yeah.
So this is your, we call this your centripetal acceleration.
Centripetal.
Centripetal acceleration. Your acceleration due to the fact that you're traveling in a circular path.
Yes.
It's called your centripetal acceleration.
Okay.
So the equation for centripetal acceleration, I can't remember how the author marks it to let you know it's centripetal. Motion in a circle. So rather than calling it centripetal, he calls it your radial acceleration. So he puts RAD there. Because it's always radially inwards, I'm always going to call it centripetal acceleration because that's what the physics book I used when I went to school called it. So that's what it's in my head as. But anyways, so your radial acceleration, that acceleration inwards, if you have to calculate it, is just omega squared times r, right?
Okay.
But now, what is omega times r?
Omega times r.
Uh-huh. Look, let's go back. Omega.
Oh, it's the velocity.
Yeah, so let's write this really quick. Let's just rewrite omega in terms of velocity. I think that'll be easier. So I know that omega times r is equal to velocity.
Yeah.
Yeah.
So I know that so I know that omega then is equal to velocity over r. You with me?
Mm-hmm.
So make that substitution in here. And what do we get? We get v squared over r. V squared over r.
Velocity squared over radius.
Velocity squared over radius. So these are your two equations. Actually, the author gives you a third one, which I've never for the life of me used, but I'll write it out here so you see it, since he gives it to you. Let me show you where it comes from. He does 4 pi squared r squared over t squared. So this is also equal to 4 pi squared r over the period squared.
Okay.
Now how do we get that one? Come back and look at what omega is right here.
Yeah.
So from this equation, I know that omega is equal to 2 pi over t.
Okay.
So omega squared times r is going to be 4 pi squared times r over t squared,
I see.
which is what he does right there. Now I've never calculated it that way before, but since he gives you the equation, that's where it comes from. Okay, this was my way of coming up with this stuff. Now I'll give you the author's way of thinking about it. So the author's way of thinking about it. So you're traveling with uniform circular motion along a circular path, which means the magnitude of your velocity vector isn't changing. Just the direction of your velocity vector is changing.
Yeah.
Yeah.
But so from V to V1, the only thing changing is the way the arrow's pointing, they have the same length. You with me?
Okay.
So uniform circular motion with some radius, he uses capital R. So we got some circle, radius capital R. You go some displacement theta. We'll call the distance between this point and this point delta x. That's not the arc length. That's the actual length between them.
Okay.
And your velocity goes from V to V1 at some time later. Good?
Yeah.
So now I'm going to redraw that V and that V1 down here.
Yep.
Yeah.
You with me?
Mhm.
And the important note, the important connection to make is that this theta and this theta are the exact same.
How do you know that?
So let's make sense of that one really quick. If you're at this side of the circle, which way is your velocity pointing?
Tangent.
Assume that we are going this way around the circle now, to stay consistent with that picture. I should have drawn my picture better. So it's going to be pointing exactly straight up, right?
Mm-hmm.
So then by the time you get over here, which way is your velocity pointing?
Straight down.
Exactly straight down. By the time you get here, which way is it pointing?
Right.
Exactly right. And by the time you get here, which way is it pointing?
Left.
Exactly left. And so if you go pi halves, your velocity changes by pi halves. So you see how for any angle of the circle you go, your velocity changes by that angle as well. Here it's pointing straight up. By the time you go, this angle right here of pi halves, it also turned pi halves.
Oh, I see what you're saying.
And by the time if you go another pi halves, it turned pi halves again.
So difference, okay.
So if your position changed by theta, the velocity's angle also changed by theta.
Okay.
Does that make sense now?
Mm-hmm.
Okay. So that was our important connection to make. So then we see that this triangle and this triangle are similar triangles. They're similar triangles because they're both isosceles triangles. This has the same length as this,
And the angle's the same.
and this has the same length as this. And angle's the same, and angle's the same, so these are similar triangles.
Wouldn't that mean that delta x and delta vector v is the same?
No, it means ratios are the same. They're similar triangles, they're not the same triangle. Let me show you two similar triangles drawn on top of each other.
Okay.
this triangle and this triangle are similar.
Yeah, but isn't...
These aren't congruent. They're just similar.
So vector v and
They're
vector
like
v1
this.
aren't the same.
These two are the same length, but they're not the same length as r.
Okay.
So we can think about this distance right here as r, and then the distance from here to here is v1.
I see.
Make sense?
Yeah.
So they're just similar triangles, so the ratios are the same. So the ratio of this length to the side length is the same as the ratio of this length to the side length.
Okay.
So this length, the length of this vector, delta v, that's what we mean by its magnitude. So its length over this vector's length, v1's length, which is what we mean by v1, just the length of v1 vector, is equal to that length over that length. You with me so far?
Yeah.
Okay. Solve for the length of our delta v1 vector.
Okay.
And it's this thing right here. You with me? Okay. So now our average acceleration by definition, if you look over there, when we went back to our average acceleration, it was the change in our velocity vector over time.
Yeah.
Right? Now we just want the magnitude of our average acceleration vector. So it's going to be the magnitude. So it's equal to the magnitude of delta. I do that every time I have to write a delta next to a v. Delta v over t. You with me?
Isn't it
Yeah.
delta t?
Yes. Delta t. Thank you. Good?
Yeah.
Now we make our substitution here. And what do we get? We get v1 over r times delta x over delta t. Just making the substitution.
Wait.
Just making this substitution.
But isn't everything over delta t?
That's the
Where's
same.
the algebra in that?
This is the exact
This
same
is
thing as
what-
v1 times delta x. Oh, you're saying, what happens if we do that over r and then we divide the whole thing by delta t?
Oh, you're just times. Okay, I see.
Okay. There you go.
Just need it written up.
Alright. So anyway, so it's equal to this, right?
Yeah.
Okay. Now we're going to take the limit as v1 approaches v. As v1 gets closer and closer to v, that gives us our exact acceleration, rather than just the average, right?
Yeah.
So we take the limit as delta t goes to 0.
Okay.
So as delta t goes to 0, your theta is also going to go to 0 because your angle will get smaller and smaller, right? And so what happens in the limit? We'll just do it one at a time. In the limit, v1 gets closer and closer to
V.
v. So that one becomes v. R is the same no matter what. It's just a constant, so r stays there. But now delta x over delta t in the limit becomes
Just V.
v, velocity. Or in other words, it's equal to v squared over r. And so it got the same thing we got.
Oh, I see. Okay.
Make sense?
Yes.
I just don't like his way of doing it. I think it's much better to make the connection that the acceleration vector is just in the negative position vector direction. But he does it this way, and he says, obviously, since the speed is constant, there's no acceleration in the same direction as velocity, so all the acceleration has to be perpendicular to velocity, so the acceleration points radially inwards. And that's his argument for that. I'd rather let the math say it.
Yeah.
So there's both ways. His derivation's in the book. Mine obviously isn't, but it'll be online. Okay, so I think that pretty much covers this chapter and then some, because everything we talked about over here and all this he doesn't talk about. But that stuff will come in handy once we get to later things. When we start talking about like sound waves, the frequency of the sound wave.
Yeah.
Oh, I guess there's one more point that he mentions here. Relative velocities. Relative velocities, he's already worked exactly the way you expect. But we'll make it make sense really quick. Position and velocity are relative. Position and velocity are relative. And so if I want to get a total position I get that by adding two positions together. So let's imagine that I've got some plane up in the sky right here. There's a plane flying through the sky. You with me?
Mm-hmm.
You're down here on the ground. Here you are. And I'm here up in the plane right here. And then here's Frank. With me?
Yeah.
And if we want the distance from you to Frank, that's the same as the distance from you to me plus the distance from me to Frank. Or sorry, the position vector, I mean, not the distance. Okay. The position of Frank relative to you is the same as the position of me relative to you plus the position of Frank relative to me.
Mm-hmm.
Yeah.
Yeah. Okay. Now, same thing with velocities. Let's reset up a similar picture. So, once again, we got an airplane completely made of glass so that you can see into the airplane.
Okay. Circular.
And I'm circular plane, obviously, aerodynamics.
Yeah.
So here I am, I'm sitting in the plane, I'm not moving. You're on the ground. You're watching me like a weirdo. Find something better to do. And then Frank's in the plane, but Frank is running in the plane. So, I don't know, how do you draw a stick person running? They're going fast. Okay, she's going that way.
Okay.
Alright, so Frank's going that way, and this is the velocity of Frank. The plane is also going this way. This is the velocity of the plane. And so Frank's velocity relative to you, let's not say Frank's running in the plane. Let's say Frank is jumping in the plane. So Frank jumps in the plane. So he's up off the ground, up in the air. You with me? So he's moving up in the plane like that. Here's the velocity of Frank. So Frank's velocity relative to me, he just jumped up in the air.
Mm-hmm.
But Frank's velocity relative to you is going to look like this. It's going to be the velocity from the plane moving, so the velocity of the plane, plus the velocity of Frank's jump.
Yeah.
So his velocity to you looks like this. Because you watch him jump, so from my position, he just jumped up and down. From your position, he jumped up and landed, because the plane traveled a lot in that time.
You're saying that's how we perceive it?
That's how you would see it, yeah. So you see right here, Frank's on the ground, and then the plane's flying forward, and by the time he lands on the ground right again, the plane's right here. So now he's back on the ground. So his jump to you looked like this. Because you can see inside the plane.
Yeah.
Whereas his jump to me just looked straight up and down. Who's right, who's wrong?
Neither.
What's his real velocity? It's relative.
It's relative to you or to you.
Yeah, velocity is relative. When you say what's the velocity, you need to say relative to what? And you usually draw some coordinate system to determine how you're going to talk about velocity.
Okay.
It was the same thing with position. Frank's position relative to me was just, I'd say he's just 10 meters ahead of me in the plane. You say, no, he's way up in the plane and 10 meters in the plane. Right?
Yeah.
Who cares? Whose position's right? I'm saying I'm going to measure his position from where I am. You say, no, I'm going to measure from where I am. Whose position is, who's measuring right? Who's measuring his true position?
There isn't true position.
There isn't? Can't we do it due to the center of the earth? Isn't that true position where someone really is?
You could do outside the earth.
Yeah. You
But we
use
can
like-
use the center of the earth as our reference frame. And that works, right?
Well, then you can use like the center of the universe.
Yeah, so you see the problem with the earth. Well, the earth's also traveling around the sun. So shouldn't we use the center of the sun and start measuring from there? You say, no, because the sun's part of the in a solar system traveling around the center of the Milky Way galaxy. Okay, use the center of the Milky Way galaxy. Well, that's one of billions of galaxies all traveling away from each other. Where should we measure position from? Now, Peter says we should measure position from the center of the universe. That's a great idea. But that makes as much sense as saying we should measure the center of the earth, the center of the surface of the earth from the center. We should measure your position on the surface of the earth from the center of the surface of the earth. Where's the center of the surface of the earth?
There isn't one.
Turns out, it makes about as much sense to ask that about the center of the universe. It doesn't have a center.
Okay.
For our current model of the universe. Who knows, maybe we're wrong. So position is relative. And velocity is relative.
Okay.
Right? Simple example that you've actually probably done before, you probably sat in the back of a truck and like thrown a ball up and down.
Yeah.
For you in the back of the truck, ignoring air resistance, the ball just goes straight up and down. But for someone outside the truck, when you throw up that ball, it goes like this. Because the truck's driving by as it goes.
Yeah, that's right.
And this is why your y, what's going on in the y direction, doesn't care what's going on in the x direction. Because from your position in the back of the truck, nothing's going on in the x direction. From someone outside the truck, a whole lot's going on in the x direction. And yet that marker still just goes up and down, and it couldn't care less that it's in the back of a truck.
Okay.
Make sense?
Yeah.
So positions and velocities are relative. And if you want to calculate the velocity relative to you, well, and we can convert between each other's velocities. Here's Frank's velocity to me, here's Frank's velocity to you, and we know how to go back and forth between these. How do you know how I see Frank's velocity? You just subtract the velocity of the plane. How do I know how you see Frank's velocity? I just add the velocity of the plane. Because when I look out the window, to me, it looks like you're going that way really fast.
Yeah.
Right?
Yep.
Anyways, so positions and velocities are relative, and you can add together the way you already expect it to be able to. And that was the last thing. Good? Alright. The next chapter will be on Newton's forces, probably the most important chapter for the whole book. We're finally going to introduce basically our postulates of classical mechanics now. All this was just getting you comfortable with definitions that we were going to use. Now we're going to introduce you to the postulates, which are axioms, or Newton's 3 laws of motion, which is what the next chapter's on.
Okay.
So, crucial chapter.